Pleasure to be here. First time in Arkansas, right? Sorry to miss the first day, but apparently we have to teach for a living. All right. So wanted to talk about some joint work with Ethan Liu, who's now a graduate student at Stanford, Jim Nolan from Duke, and Hongyi Zhu, who's now a graduate student at Michigan. Both Ethan and Hongyi were undergrads at CMU. We did some of this while they were still undergrads. And I guess in the beginning, maybe I'll spend one or two slides talking about some older work with, which is joint work with Andre and Xiao, right? So this was mentioned, a lot of the things I'm going to say were mentioned many times in this conference. Let me just see if I can focus quickly on something slightly different. So first, Simming talked about Keller-Siegel, right? And how you use the dissipation enhancement to defeat nonlinearities, right? So so he's spoken a lot about that. Let me just give you a quick summary of one idea on how you can actually use it, right? So just to remind you of the equation, so since Simming introduced it, this was Keller-Siegel equation. Rho is the concentration, population density of some bacteria, right? I have a diffusion term, and then I have a nonlinear chemotaxis term, right? So the bacteria secretes a chemoattractant, and then the evolution of the population is governed by either diffusion out from regions of high population or a concentration, a bias based on the concentration of the chemoattractant. And that's the nonlinear term on the right-hand side. Right. And of course, he mentioned there's this competition between diffusion and the aggregation, whichever wins. According to that, there may be a blow-up. And there are these sharp results that say, hey, look, there's a blow-up in this equation if and only if your integral of the initial population is greater than or equal to 8 pi, right? So if you add advection into the equation, all right, you can use the enhanced dissipation to beat the nonlinearity, right? Again, Anna did this also for the Kuromoto-Shevardnadze, which was one order higher. Let me give you one different idea on how this proof works, which is a little bit different from what Anna just said, right? So I add the convection here. So time derivative of rho plus the convection term in blue minus Laplace rho. I put coefficient 1 in front of Laplacian for now, and your standard nonlinearity, right? Again, since many of these were mentioned before in the talk, let me not say so much, right? There's these old works of Sasha Kislev and Xiao that say, okay, I can choose U amongst a certain family to stop the blowup. There are these works of Simming and Bedrosian and Tadmore, right, that can use shear flows, etc. To do this using just enhanced dissipation, let me do the following, right? So this is this idea from me, Andrzej Latosz, and Xiao Xu a few years ago, right? I'm going to call T-dis the dissipation time. There's a reason I'm using this. I'll say this using this notation. I'll say this in a minute, right? So this dissipation time is exactly what Anna said, right? Simming called it T half, right? So let's look at the linear operator here, right? Look at the solution semi-group of that. I know it's a contraction in L2. How long do I need to wait until this contraction has norm less than, let's say, delta, right? Put delta equal to half. The amount of time I need to wait until this contraction has L2 norm less than half is called the dissipation time, right? L2 dot is just L2 with mean 0, because if I don't exclude mean 0, it's not a contraction, right? Those constants are preserved, right? What we can prove is I say, hey, if your dissipation time of this advection diffusion operator is small enough, yeah, then you have global regularity, right? No blow up. So this is similar to some of these results that were mentioned before. Let me tell you the proof. It's just one page, okay, and it's super quick. All right. Here's a sketch of the proof. Why does it work? Okay. So whatever the nonlinear equation is, let me rewrite the nonlinear equation as one time derivative plus your enhanced dissipation term and a nonlinear term on the right hand side. So what am I doing? I'm fighting with the possibility that the nonlinear term could cause a blowout. What do I have going for me? The first thing I have going for me is, let's use the energy inequality, right? So multiply by theta, integrate by parts, this convection term goes away. Integral of theta Laplace theta, that becomes integral of gradient theta squared. That's a good term with a nice sign on the left-hand side, right? So if integral of gradient theta squared beats the nonlinear term on the right-hand side, which is integral of theta times nonlinearity of theta, right? Then I'm in great shape, right? Because left-hand side will cause me to decrease, beats the growth I get from the right-hand side. So that's the first statement I make, right? So look at integral of theta times the nonlinearity, do some Sobolev trickery, right? Integrate out. You can bound that by norm of theta to the fourth and norm of theta to the square, fine, right? That's your right-hand side. The thing you got from the left-hand side is here, integral of gradient theta square. If that beats the right-hand side, you're in great shape. You don't have to worry. What if not? Yeah. So suppose my integral in time of the left-hand side was smaller than this quantity on the right. Fine. So let me just write down the equation through Duhamel's principle. Theta at time t is just the linearized semigroup on your initial data plus the nonlinear time convolution, right? So integral in time of semigroup applied to nonlinearity at time s. Integrated in S. Okay. Now I'm going to do this up to the dissipation time. What do I get at the dissipation time? At the dissipation time, my linear operator caused my L2 norm to drop by a factor of half. So amongst these two terms, the first term gives me a factor of half. If somehow I could guarantee that the second term was also less than half, I'm in business. All right, what do I have going for me in the second term? It's an integral of 0 to t dis. If t dis is small, hey, that's an integral of a small time interval, right? So I have something small coming out in front, so I wrote that here, t dis. Yeah. How about the rest of it? Well, it's the norm of the nonlinearity. How do I control the norm of nonlinearity? Controlling nonlinearity by L2, that's not going to work out. But I have something going for me. I assumed that the H1 norm is small already, because if H1 norm was large, I'm not in trouble at all. So can I control nonlinearity in terms of the H1 norm and the L2? If my nonlinearity is nice enough for me to do that, I'm in great shape. So if I can bound the nonlinearity by, let's say, H1 norm and then some large power of norm in theta and L2, right? Then instead of H1 norm, I can use this guy, right? I bound everything in terms of an L2 norm, maybe to a large power. And t dis is small, it sits outside that integral. So if I can make now the second term less than half, L2 norm doesn't grow. And if my equation is nice enough that L2 norm doesn't grow and price don't blow up, I'm in business, right? So that's the simple idea. That's all you need. So if you're dissipation enhancing, as long as your nonlinearity is reasonable, you can beat it. So why did I want to start with this? I say, okay, this is one example of how you can use enhanced dissipation in the study of some nonlinear equations. Of course, you can do it to other equations like Kromatov-Shevchinski, Carnegie-Melon, right, etc. So let me talk about how you would, bounding enhanced dissipation, right? So if I just go back 1 second, right? The theorem says, hey, if the dissipation time is small enough, then you can beat nonlinearities. So I need to give you examples of flows where dissipation time is small enough. And thankfully, a lot of these were mentioned. But let me mention them in a slightly different way. Okay. So here, so in Keller-Segal, I put 1 in front of Laplacian. Let me go back to the standard convention of putting kappa in front of Laplacian. Okay. So if I have kappa in front of Laplacian, now again, dissipation time is exactly what I said before, right? Look at the norm of the linear semigroup, L2 means 0 to L2 means 0. How long do I have to wait until that drops below some number, delta? Okay. Think of delta equal to half. I call it dissipation time because I saw this old paper by Fan Zhang in 2003, and I like the name, right? So that's where I got the name from. There are a couple of other things which we can state, which are very related, right? So one is, instead of looking at the norm of this linearized operator from L2 means 0 to L2 means 0, I could look at it. I guess the strongest norm would be if I put initial data, if I look at the norm from L1 to L infinity. Right? So how long do I need to wait until this operator norm in L1 to L infinity drops below a constant value? Right? Okay, I don't know if there's any name for this. We used it in our paper with Andre and Xiao to quench reactions, because when you're quenching reactions, it's the L infinity norm you care about. And this is really the strongest one that we look at, right? So let me call that tau star, right? Then there's this other notion for probability, which has been used widely by all the probabilists. It's this notion of mixing time, right? Let me state what the mixing time is in PDE language, right? In PDE language, I say, hey, look, let's look at the linear operator and call P the fundamental solution. Okay. So if P is the fundamental solution of this equation dt minus L, right? I say, okay, after a long time, right, if I'm doing things on the torus, I expect P to converge to the constant 1. Because U is divergence free, Lebesgue measures, right? So if P converges to the constant 1, the mixing time is, I say, okay, how long do I need to wait until the L1 norm of the difference between fundamental solution and the equilibrium state, which is 1, is below a constant number, right? Think of delta as half, if you like. So mixing time is convergence in L1 of the Green's function. Right? So I say, okay, of course, this has a probabilistic interpretation. Instead of looking at the PDE, I could look at the SDE, dx equals u of x dt plus square root of kappa dw, right? If you notice, I put kappa over 2 in front of Laplacian, right? This is this unfortunate thing. If you do it in probability, extra half factor shows up, right? So generator of this SDE is exactly that linear operator over there, right? If U is divergence free, it means that the Lebesgue measure is preserved, right? I'm going to do this on the torus. So I know that my stationary distribution of this stochastic process is just the Lebesgue measure. How long do I take for any arbitrary initial distribution to get close to the stationary distribution? That's the mixing time, right? The probabilists always measure the distance in total variation norm. But for us, our noise is non-degenerate, it's Brownian motion. So I know that any positive time, my distribution is smooth, right? So instead of total variation norm, I can just do the L1 norm here, and this is perfectly equal. Okay. So, all right. So what are the relations between each of these, right? So there's the L2 norm that we've talked about a lot. This tau star, which there's no name, right? And then there's the mixing time. Yeah. So first, if I look at any Markov process, this choice of delta over here is just arbitrary. It doesn't matter, right? So instead of delta, if you wanted to look at delta prime, right? So mixing time to reach level delta prime, I can relate in terms of mixing time to reach level delta times a constant, which is log of delta prime base delta, right? And you can work these out explicitly. It's just the consequence of Markov property. Right? How do I relate mixing time and dissipation time? Right? So this is again quick, right? If I tell you that I have a bound on the mixing time up to an explicit constant, right? In this case, log 2 to base delta. The dissipation time is bounded above, right, by a constant times the mixing time. And this is true in any Markov process. You don't even need assumptions of non-degeneracy of the noise. So the mixing time is a stronger notion, right? That this is what the probabilists use, right? And of course, this tau star over here is even stronger, right? It's bounded with by constant 1 above from the mixing time. Now, of course, if we want to go in the other direction, if I want to bound the mixing time by the dissipation time, then I need an assumption. I need to say, hey, look, if the noise is non-degenerate, then the mixing time is actually bounded above by a constant times the dissipation time times log of kappa times dissipation time. So why is this? You can visualize this very simply, right? So mixing time, if you like, think of as I have convergence in L1, right? Dissipation time says, well, if you give me L2 initial data, then after this much time, I can drop the L2 norm by a factor of half. For mixing time, I start with a delta distribution, right? I know because my noise is non-degenerate, immediately it becomes smooth. So let's say L1, right? So after a little bit of time, my distribution becomes L1. Yeah? Now, in order to use something about the dissipation time, I need to make this L2. So if my noise is non-degenerate, or if my diffusion operator is non-degenerate, if I wait for time 1, right, I'm going to become L2, but with a large norm. So if I have L1 norm 1, wait for time 1, I'll become L2 with norm like 1 over kappa to half dimension or something like that. So now I have this guy with an L2 norm that's huge, 1 over kappa to half dimension. How long do I have to wait to kill that in L2? Well, log of kappa to half dimension. So that's this extra thing. So this is somewhat quick. You can say I can bound mixing time above by dissipation times log of kappa dissipation time, right? I don't think this is optimal. Probably you can do a little bit better, but this is what you can get essentially for free, right? So same thing, you can bound, right? So I don't know why I wrote the second one. Okay. Second one is unfortunately I cut and paste a bit hastily. The same as the first one. Right? All right, so what's enhanced dissipation? We've talked about this a bunch, right? So I know that the dissipation time is bounded above by constant over kappa. These other two things I wrote, which is mixing time and tau star, those are also bounded by constant over kappa, and that's not hard to show. Right? Enhanced dissipation, just to clarify my convention, whenever I say T dis without a delta, I mean T dis of half, right? Same thing with T mix and tau star, right? So enhanced dissipation is when the dissipation time T dis is much smaller than 1 over kappa, little over 1 over kappa. And of course, we have the usual intuition, which has been said many times, right? What happens? The convection moves energy to high frequencies. When I go to high frequencies, Laplacian works faster. Right? So if I have this combination between convection and diffusion, I should be able to dissipate much faster than if I had just diffusion alone. Right? And these blow-up suppression results I mentioned before says, okay, if you give me enough sufficiently enhanced dissipation, then you can stop blow-up suppression, etc. So what are examples, right? So this is completely not comprehensive, apologies, and most of them have been mentioned so far already, right? There was the old Konstantin Kiselev-Rizhik-Shlatosh thing that says, hey, look, if U is time independent with no H1 eigenfunctions, then your dissipation enhances. If you're a shear flow, right? Well, I learned recently it's first due to Kelvin, thanks to Swimmingstock, right? Right. But shear flows, you have a dissipation time to be something polynomial, right? Constant over kappa half or kappa cube, depending on the singularity of, the order of vanishing of the shear profile, right? Cellular flows. In fact, I'll talk a little bit about cellular flows. So what we did in our paper with Andre and Xiao was I say, hey, look, we were trying to stop the blow up in Keller-Segal and other nonlinear equations. And all we wanted is one family of flows for which you can have arbitrary small dissipation time. So we showed that, okay, you can take a cellular flow and rescale it appropriately to make the dissipation time as small as you want. Right? So that's an existential result. But I wasn't happy because cellular flows are, I mean, they're very concrete. Right? You have a cell size, you have a flow amplitude. You should be able to bound the dissipation time explicitly in terms of the flow parameters. So we went back and did this with Hongyi Zhao, right? While he was an undergrad at CMU. I have an explicit bound. I'll show you how that works. The reason I want to show you how that works is also the proof is slightly different from the PDE proofs. So I'll say that in a little bit. Right? And then mixing flows. Mixing flows have been mentioned before, right? For mixing flows, I know that the dissipation time is bounded above by log kappa square. And then because of these inequalities I wrote before, right here at the bottom, if dissipation time is bounded above by log kappa square, for the mixing time, you just pay an extra log kappa. Yeah. So for these mixing flows, right, I can bound dissipation time by log kappa square and mixing time by log kappa cube. Right? This is not optimal. I think the right bound is mixing time is log kappa and dissipation time is log kappa. Yeah? So Sam, Jacob, and Alex have examples of nice things where you have dissipation time of order log kappa. Right? So I don't know if you didn't, as far as I can tell, you didn't look at mixing time in your papers, but I suspect that you can get mixing time also log kappa using your methods, right? Right? Probably requires some work, right? Then, of course, there was this alternating tent shears paper of Tarek recently, where the dissipation time was of order log kappa. Of course, it implies that the mixing time is log kappa square, but I suspect, again, mixing time is probably log kappa over here, can probably be proved. One thing I'll talk about is this work that we did with Jim Nolan and Ethan Liu, right? Is if I look at a discrete time example, right, where phi is a piecewise linear Bernoulli map, I'll say what that is, right? It's a version of mixing that's easier to work with, right? Right. So in that case, you can get sharp bounds. You can get the mixing time to be of order log kappa, and hence the dissipation time and all the other ones are also of order log kappa. Right? I'll tell you how this works in a little bit. Of course, I expect that anytime you're exponentially mixing, the mixing time is bounded above by log kappa, but as far as I know, there's no proof, right? And the other direction, if mixing time is log kappa, does it imply exponentially mixing? I don't know, right? As far as I know, there's no general, all examples satisfy this, right? But as far as I know, there's no proof, right? All right, so how does it work for cellular flows, right? Yeah.
You have like double expansion.
Right. So even for a total automorphism, mixing time is log kappa. I know it, right? So there's a way to state that you have double exponential convergence, and that's what look at what T mix of delta is, right? So instead of looking at T mix of half, look at T mix of delta. Normally, I would say T mix of delta should be whatever T mix of half is times some log delta stupidity. But if you have double exponential convergence, it's much smaller than log delta, right? So we can prove that for these Bernoulli maps, we can do a little bit, right? But in general. All right, so cellular flows. So how do cellular flows work? Here's a picture, right? So I just look at the torus, right? And this is basically a strong array of opposing vortices, right? So each one, think of streamlines going in a circle like this. One of them clockwise, next one counterclockwise, right? So the blues are clockwise, the greens are counterclockwise, just drawn streamlines, right? So let's put parameters. Let's call the size of one of these cells epsilon. Yeah. And then the amplitude of the flow on those streamlines, call that A over epsilon, right? So just to put explicit formulae, I'm looking at a Hamiltonian H, which is sine of 2 pi x over epsilon, sine of 2 pi y over epsilon. That's the Hamiltonian. Velocity field is the skew gradient of the Hamiltonian. And there's this C in front of the Hamiltonian here, which I have for technical reasons, which believe me is not necessary, but it simplifies the proof a lot. Okay. So let's ignore the C for now. Right? And I'm going to look at the mixing time from a probabilistic perspective. So look at the diffusion dx equals A times V of x dt plus square root of kappa dw. A is some large number, which I like to call the amplitude. So technically, if I put in here, since V is grad perp of this guy, grad perp of this guy will have a 1 over epsilon in it. So the amplitude is A over epsilon. Okay. So my goal is to make the mixing time small. Well, whatever I state is going to work in the following parameter regime, right? So I need epsilon square over kappa. So that's the size of one cell over diffusion to be small. And I need A to be larger than 1 over this guy. Okay, I'll tell you why in a second. Epsilon square over kappa being small is actually the only region of interest. I like that, right? So what's the mixing time? So I can tell you that, well, there's 2 different parameter regimes, right? So unfortunately, the version on the archive doesn't have both these parameter regimes, but I promise that will be fixed very soon, right? So in one case, when A is much, much larger than kappa over epsilon to the 4, I claim that the mixing time is bounded above by just epsilon square over kappa, right? And in the other case, right, when A is smaller than kappa over epsilon to the 4, I claim that the mixing time is bounded above by 1 over square root times kappa A. So why is this, right? Let me say where these numbers come from, right? So if I look at one small cell, forget the rest of the torus, just one small cell. I start a particle inside one of these cells, and I ask you, how long does it take to get out of one of these cells, right? Or just in PDE terms, right? If you put a point source of heat in one of these cells, how long does it take for the temperature to be roughly uniform in one cell? Right? Well, in one cell, right, the flow is just going around in circles. All diffusion that happens transverse to the flow, right, happens basically due to the diffusion kappa. Right? So, well, now due to diffusion kappa, I need to travel a distance of epsilon. How long is it going to take me? Epsilon square over kappa. Right? So the time to even things out in one small cell is epsilon square over kappa. Yeah. And now I'm telling you, if capital A is very, very large, all I need to do is even things out in one cell, and then just even everywhere. Right? So that's the first parameter regime. If capital A was not so large, the second parameter regime, there's actually a reasonable explanation for where this number comes from, right? I know that if I have many, many cells and I zoom out, this theory of homogenization works, right? This whole thing behaves like an effective diffusion with a certain effective diffusivity. What's the effective diffusivity? It's exactly square root of kappa times A, right? So what I'm telling you in the second regime is that homogenization, quote unquote, works. And if homogenization works, my mixing time should be 1 over the effective diffusivity, and that's the second bound. So, all right, so whatever these exact bounds are, let me tell you where the proof comes from. Right? Right. So, I mean, I've spent my entire life as a PDE person, and all I've done is integrated by parts. So, this is one slightly different idea. Right? I bound the mixing time using a coupling argument, right? Which is a nice idea from probability. Right? I say, so how does coupling work? I say, take your diffusion, take 2 copies of your diffusion. right? So I'm drawing, so one guy, this red dot over here, and that's the green trajectory. The other guy is this blue dot over here, sorry, the red dot over here, and the blue trajectory. So I'm taking two copies of the process with just different initial points. Okay. Now, what are my rules? For each copy of the process, it should still satisfy the same equation, right? So W should be a Brownian motion, right? And it should still satisfy dx equals u of x dt plus square root of kappa dw. However, there's no rule saying the Brownian motion I use for the first one should be independent of the one of the second. Right? I'm just saying that each one on its own is a copy of the original process. Right? And then there's this fantastic bound. Right? I say, hey, look, take two copies of this process, choose a noise for each of them as you feel like, right? And wait until they meet. So you can see over here, and these trajectories are drawn, they meet at that purple dot. Ask you, how long do they take to meet? Right? This is called the coupling time. I call that tau couple over here. So there's a fantastic bound in probability that says the mixing time is bounded above by a constant times the coupling time. The proof of this is again like 3 lines. Okay, it's super simple, but this whole concept of coupling is wonderful, right? If you can couple, right, you can bound the expected coupling time, then for free, the mixing time is bounded above by the expected coupling time. So if I can cook up the noise for these two processes in a way to make the coupling time small, I'm in business. I've got a bound for the mixing time without integrating by parts. Right? So I'm happy. Yeah. So how do we do this? Right now, well, let me just give you the intuition rather than going through the details. Right, the intuition behind bounding the coupling time here is I say, okay, first I have to wait time epsilon square over kappa to get out of one cell. There's no negotiation with that. Right, that before I get out of one cell, this process and that process, they just don't. Fine. Once I get out of one cell, right, there's this thing. If I'm close to the boundary layer, so the boundary between two cells, right, every time I cross this boundary layer, I essentially perform one step of a random walk on this lattice of cells. And again, how does this work, right? You see, if I'm super close to the boundary, I can say if I'm super close, there should be a thin enough region where the time it takes me to jump from one cell to the next cell is comparable to the time it takes me to go around one cell. And if that's true, then I can say, hey, look, maybe in this time, either I've jumped across or I've gone around a little bit. So if I've gone around a little bit, it's not sure whether I jump across over here, or I jump across over there, or I jump across over there, right? So it's not sure. So if I balance these two effects, I'm really jumping randomly to one of the neighboring cells. All right, so if you buy that, I say, okay, a crossing of the boundary layer is like performing a random walk on this network of cells. How many cells are there? Well, 1 over epsilon in each direction. If I have a random walk on a lattice of 1 over epsilon by 1 over epsilon, probabilists have studied this to death. They know how to couple, right? If you give me a random walk on this big lattice, I can do this coupling by reflection. Whenever one guy moves up, make the other guy move down. If this guy moves left, make the other guy move right. Just do this mirror trick, right? I know what the coupling time is. So if I just use this intuition, I can say, hey, look, random walk couples after time 1 over epsilon squared. I just need to estimate how much time I need to wait to perform 1 over epsilon squared boundary layer crossings. Right? And since this problem has been studied to death, there are estimates I can just quote from previous papers, right? Let's say this is how long you need to wait, right? And then, of course, there's some technical issues because it's continuous in space, continuous in time. That's why I had that cutoff function, right? And you can make everything work. So,
It was a couple of the boundary cut, or it sounds like you're saying this is how much time it takes before they're in the same cell.
Right. So there's a bit of a catch, right? If I just put both of them in the same cell, right? So in one cell, I know that the mixing time is epsilon square over kappa. I don't know that the coupling time is epsilon square over kappa. I just don't know this because the amplitude is really large. That's the reason we had to put this cutoff, because if you're in the center of the cell, then you have no velocity field, right? And then I can couple it nicely, right? So there's a bit of a catch. But thankfully, through our construction, they'll actually meet at the cell boundary. I just need to pay this initial time with the cutoff function, right, to start off the coupling. Right? But yeah, right. All right, so that was idea one. Let me see if I can talk a little bit about idea two, which is the discrete time problem. So this discrete time problem, I say, hey, look, instead of running everything in continuous time, I'm going to do the following. So call x at time n+1 to be some map phi applied to xn plus a little bit of noise. Right, so epsilon times zeta n+1. So this is the probabilistic version. So what am I saying? This is the time split version of the old SDE I had, right? dx equals u of x dt plus epsilon dw. Epsilon is square root of kappa. U of x dt, right? Well, if I look at the deterministic dynamical system, x dot equals u of x, right? Look at the flow map after time 1. That should be what phi is, right? So in PDE language, I'm telling you, run the process where theta n+1 is equal to theta n composed with phi, which is solve advection for time 1, and then solve diffusion for time 1, right? No advection. And this is the probabilistic version. Okay. So I put epsilon equal to square root kappa for convenience. Epsilon times zeta n, these are all random variables on the torus. I just need their mean zero, and their quote unquote length scale is of size epsilon. Of course, they could be periodized Gaussians, and then you would get Laplacian back, and that's fine. Yeah. So what's our motivation, right? Motivation is if I looked at a map phi, as opposed to something that comes from a flow, there are more examples, right? These examples, it's just easier to work with. So again, as I said before, I expect that if phi is exponentially mixing as a dynamical system, then by exponentially mixing as a dynamical system, it's exactly the same as saying that the flow is exponentially mixing, right? This implies that the mixing time should be bounded above by log epsilon. There's no theorem of this form, right? But that's what I expect. So far, we only have dissipation time log epsilon square, mixing time log epsilon cube. What we can prove is in this example, where if phi is a nice piecewise linear or piecewise affine linear Bernoulli map, then the mixing time is also of order log epsilon. So I'll show you what a piecewise affine linear Bernoulli map is. I'll tell you what the basic idea is in a second. Right? Actually, we can do a little bit more. Not only do we get mixing time to be of order log epsilon, we can also say dissipation time is log epsilon, and we can get explicit constants from both above and below, right? All right, so what is this map, right? So what I'm going to do is I'm going to take the torus, divide it into a bunch of subdomains, right? So here, I guess, 1, 2, 3, so 5 blue squares and 1 reddish square, right? And on each square, I want the map phi to be a linear bijection from this square to the whole torus. So it's like, I guess it's an asymmetric version of your doubling. First map you see in mixing in dynamical systems is the doubling map on the unit interval, right? Now, instead of, so doubling map sends 0 to half to the whole interval, and then half to 1 to the whole interval again. If you want to study the doubling map, you can do this through Fourier transform and get everything you want, mixing time, blah, 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 right? If instead of doubling map, you make it slightly asymmetric, this proof breaks. You need something else, right? So that's what we were trying to do. I say, hey, instead of doubling map, I can also do it in higher dimensions. If I make things slightly asymmetric, like the picture I've drawn here, the Fourier transform proof breaks. I need to do something else. And that's what we're doing, right? So our result is the following. I can give you a bound for the mixing time, both from above and from below. Above, I can tell you, is a constant times log epsilon. From below, I can tell you the exact constant, right? So it's like log epsilon divided log of the measure of Emax. Okay, so sorry for this notation, but when you do probability, there are a few rules you have to follow. Rule 1 is that if you have a stationary measure of a Markov process, it has to be called pi, right? Otherwise, right? So pi of Emax, so E is for each of these domains. Emax is the largest one of these domains, right? So if I take log epsilon over log of pi of Emax, that's the sharp constant in front of log epsilon that bounds the mixing time, right? And it's unfortunate because even in this simple situation, you see, okay, I get the right power of log epsilon, but I'm not able to get the right constant. Right? So if instead of mixing time, I looked at the dissipation time, right? Then I can get explicit constants, but they don't match. Right? So if I look at dissipation time, the upper bound is log epsilon divided by log of the measure of the largest subdomain. And the lower bound is log epsilon divided by log of the measure of the smallest subdomain. There's a gap, right? And I don't think this gap, right? I think this is sharp, right? Okay. So, all right. What's the idea behind the proof, right? Again, so I guess theorem 2, where I don't use integration by parts, so I'm happy, is the following, right? So first, I'm going to take the torus, and I want to divide it up into a bunch of small domains whose diameter is of size epsilon. Okay? And these are not just arbitrary domains, these are domains where powers of phi are piecewise linear. So, I mean, if I go back, you see, phi was linear on this big square. Now, if I look at phi square, right, phi square is going to be linear on a bunch of smaller domains, right? So each of these domains I need to divide up into smaller squares and see where phi square is linear. And then if I look at phi cube, it's going to be piecewise linear on a, like I divide the torus into smaller and smaller domains, right? So I do that over here, keep dividing until each of these domains has order epsilon in diameter, and phi is, well, some large power of phi is linear on each of these domains, right? And if you look at the rate at which phi expands, right, you're going to see that, hey, the power of phi you need is going to be of order log epsilon. So what do I have, right? On each one of these small domains, if I take phi to nth power, where n is log epsilon, right? Phi basically maps one of these small things to the entire torus in a defined linear way. Right? So okay, say that over here. So if, hey, look, if my initial distribution was uniform on one of these small pieces, right? I push forward this initial distribution by my map phi after n steps, I just get the invariant measure on the torus. Right? But unfortunately, this is just a blind push forward of the initial distribution by phi, ignoring the noise at each step. If I add the noise at each step, I don't know if I ask you what's the difference between the distribution of xn and the invariant measure, this may not be small. At least we can't prove that it's small directly. Right? So we had one trick over here, which is I say, hey, look, suppose I could find a function f. I call this fs. So fs is something such that it's supported in each one of these small domains, right? And it's such that if my initial distribution is fs, then after n iterations, my distribution is bounded below by a constant times the Lebesgue measure. If I could find such a function f, right, then what I'm going to do is I'm going to say, hey, give me any arbitrary initial distribution, right? After time 1, immediately, because my noise is non-degenerate, it regularizes to something smooth, right? Whatever the smooth thing is, I can write it as a combination of my bump functions fs. If I write it as a combination of my bump functions, capturing, let's say, some small fraction of the mass, right? then I can say, hey, look, each of these distributions, when I push forward after n iterations of the Markov process, they get bounded below by some constant times Lebesgue measure. So when I do this whole thing together, hey, distribution after n plus 1 steps is going to be bounded below by, oops, that shouldn't be over delta, but okay, times delta square, sorry about that typo, right? So distribution after n steps is bounded below by a constant times Lebesgue measure. And once you do this, right, you can do the same sort of coupling argument and say this immediately implies that your mixing time is of order number of steps divided by that constant. So begin over delta. Right? So this is a standard sort of trick that you have, or this is the standard game you play when you want to show things are mixing and probability. Right? Okay, so this was our idea, and this all works if we could find a bump function f that had these nice properties. Right? So how do you find this function f? This is a bit of a pain. So to find this function f, right, just by scaling, I claim is enough to do the following. Right? I find like one continuous function, let me call it f0, whose integral is 1. It's supported on the unit cube and it's continuous. Okay. And if I take the distribution of the noise, let's call that k epsilon. So k epsilon convolved with, sorry, that should be f0, my bad. So k epsilon convolved with f0 is bounded below by f0 times 1 minus a little bit. So it's like you convolve it with the noise a little bit, and then the level drops, but by a multiplicative factor. So if I could find a function f that satisfied this simple convolution inequality, right, then I can make the rest of the proof work. So this looks innocent and like, okay, you give it to an undergraduate student and he should come back with an answer. Unfortunately, it stumped us. Okay. If your dimension is 1, you can find f to be just be a 10th function, no problem. If your noise is a Gaussian, you can choose f to be a principal eigenfunction of the Laplacian, and then you can just quickly use the maximum principle to check this inequality is true with a equal to 1 and gamma equal to 2, right? But if not, right, if your noise kernel is, I don't know, it's a product of one-dimensional noise kernels, then I can use my one-dimensional calculation to get something, right? But in general, if my kernel is just something reasonable, symmetric, and non-degenerate, I don't know how to do this. So, yeah, right. So that's one unfortunate thing that we're stuck on, right? But all right, so this is a quick thing on the mixing time bound. The dissipation time bound, maybe I can say that real quick as well and stop. The dissipation time bound works through ideas that are, I guess, more familiar to me, right? Bound the dissipation time. Okay, so let me call theta n to be ex of theta 0 composed with xn. So this is just like take an initial test function theta naught, hit it with your semi-group after n iterations, and assume that your mean 0 to start with. So dissipation time is how long I need to wait until L2 norm of theta drops by a factor of half. So here's a lemma. Right? I claim if theta naught is regular, right, which is gradient of theta naught is bounded above by 1 over epsilon times the L2 norm. In that case, I claim that after n iterations, L2 norm drops by a factor of half, provided n is at least log epsilon divided by log of pi v max, right? Explicit constant, up to some additive constant c. Okay. Apologies, this should be plus c and not minus c. All right. So if you give me the lemma, right, then immediately you say, I see a way to prove the theorem, right? Because if you start with an arbitrary initial theta naught, because noise is regular at time 1, it immediately becomes H1. But even though it becomes H1, I pay a price. The H1 norm becomes of order 1 over epsilon. I don't mind, right? Because in my lemma, if the H1 norm is 1 over epsilon, no problem. You just wait for log epsilon by log pi V max time, and then you're golden. The L2 norm drops, right? So, okay, so if I had the lemma, I can make things work. How do you prove the lemma, right? Well, the idea behind the proof of the lemma is I say, okay, divide up your domain into each of these cubes as we had before, right? And write theta naught as sum of indicator functions on these cubes plus something small. Why can I do this? If my gradient is of size 1 over epsilon times norm of theta naught, right? Then as soon as my gradient is this is basically a Poincare inequality argument, right? So as soon as my gradient is of order 1 over epsilon, on sets of size 1 over epsilon, my function doesn't oscillate too much. My function doesn't oscillate too much on sets of size 1 over epsilon. I can approximate by a constant on sets of size 1 over epsilon. And that's what I'm doing here. See, okay, so I use my assumption to say theta is a sum of piecewise constant things plus something small. Okay. Now, the small catch over here is that I need to insist that the diameter of these sets is a big constant lambda times epsilon. Right? So lambda is like 100 or something like that. So what can we prove? I say, okay, if this constant lambda is large enough, and you start with initial data to be indicator function of one of these sets, wait for time log epsilon over log n, right? Then L2 norm drops by a factor of half. Right? And okay, this is intuitive, but it's a little bit technical because I know that after n steps, phi maps one of these steps to the whole torus. I just need to make sure that the error I make due to the noise at every step doesn't spoil things, right? So that's why I needed lambda to be large. There's some technical convolution in estimates. But once I do this, if I combine observation 2 with observation 1, I have the proof of the lemma that implies it, right? So that was all I wanted to say. I mean, I have a bunch of references, which I'm happy to share, right? So thanks.